All right, we've got about 10 seconds for Advent of Code Day 5. We've done both parts all days so far, but at this point, it's good to remind people that you do not need to do both parts every day. Doing part 1 is enough. Make sure that you pace yourself as we get through, day 10, day 15. There's 25 days of this, so it is quite a lot of work. So, day 5 is Print Q, a very familiar printer, 2017 day 1. The new Slay launch safety manual. New pages need to be printed in an order. The notation XY means that if both page number X and page number Y are to be produced, page X must be printed at some point before page Y. The elf has for you both the page ordering rules and the pages to produce each update, but can't figure out whether each update has the pages in the right order. Okay, so there's two parts to the input today. Our first split input. First section specifies the page ordering rules, one per line. First rule means that if an update includes both page number 47 and 53, then page 47 must be printed before page 53, and it can be anywhere before that. Second section specifies the page numbers of each update. The first update is the first line. To get the printers going as soon as possible, start by identifying which updates are already in the right order. The first update in this example is in the right order, so we need to get all these rules into some kind of structure where we can access them by page number. So I'll probably end up going with a hash map here. Other people that do more optimized work would probably use a vec or a vec of vecs in this case. Because the first update does not include some page numbers, the ordering rules involving those missing page numbers are ignored. For some reason, the elves also need to know the middle page number of each update being printed. Because you are currently only printing the correctly ordered updates, you'll need to find the middle page number of each correctly ordered update. So for part 1, we just need to apply the rules, or not apply the rules, but check to make sure the rules are valid for every number as we go through. So we should be able to kind of iterate our way through slices or sub-slices of this. So we start with 75, or we can actually pop the head off too, if we want to. So we could use like a vec deck for these. Pop the head, check the rules against the rest. Pop the head, check the rules against the rest. And that'll be nice because if we pop the head and then check the rules against the rest, we could just do like dot contains or something like that. So I guess let's get started. We need this input. Just create day 5. And then we've kind of got these rules, which I think I'm going to put into that hash map. That sounds correct to me. Having kind of a vec of numbers that need to go after this one. So I'm going to start with using nom here because it just starts to make these kinds of things easier once we start having multiple inputs or multiple things to parse or sections to parse in our input. What is our answer for this? Our answer needs to be 143. So I'm thinking about going with a fold many for this. I think I'm going to change these U sizes actually to U32s. We're never going to have a U-sized thing, so we don't really need it. So we end up with a rules parser. That is the first section with a fold many 1, separated pairs. We can include the line ending here as well. Notably, I switched from using new line in the earlier videos to using line ending. It's the same thing, except for the fact that line ending works cross-platform because it's not just a new line literal. So when we have our hash map here, we're going to get these items in, and these items are going to be tuples. One of these will be the page ID, and one of them will be the after page. So we can use the entry API, which is great, to grab that page. And that will theoretically give us a vec that we can then just push into, or we want to insert a new vec with the after in it. And we can grab our parse function up here and do our input. And I think at the end of the day, our parser is going to return the set of rules and the set of updates. We haven't typed it to be that yet, so I think we will, I guess the updates are going to be a vec of vecs, and these are also U32s. So this will now get called. We'll look at the rest of the input up here and then whatnot. So we should have our parsed rules now. And that kind of leaves us with the rest of the input. So we'll need to do a new line here, and then we can do each of the updates. So we'll just add that line ending in our parser. And then this is going to be 2 separated lists. We don't really have to break this out, right? We could write this more concisely, but it does let us get this separation here. So theoretically, if we had an issue with this parser, we could go test it. This parser in particular is kind of too simple for that. And here's our parsed updates. So we've got 75 through 29, and the last one is 97 through 47. So I think we're good here. So our return value changes to be the input, the parsed rules, and the parsed updates. So we should have those up here ready to go. As just a reminder, we have the hash map of the rules so that we can do get lookups into them. And then we have all of the updates because we're going to iterate over them. And input should be empty, so we're just going to ignore it with our underscore. So how did I say we were going to actually do the logic here? I think we're going to pop off the first one, which means that we need to pop the head off. So we're going to iterate over updates. And for now, we'll just kind of collect it. One really cool trick here is that we can use an underscore in this type to actually just let the Rust compiler infer it. So for each update, we get the list. We need to pop off the front though, for this strategy to work. I think we also want to enumerate this because that'll give us our index. And I think here we can filter. Specifically, we can probably filter map. So we'll start off here by shadowing update and calling it a slice into this vec. We can do that with this syntax. So we have everything here, but actually we want everything after. And what we actually want here is the 0th item of update. And I'll just throw a none in here for a second. Actually, you know, I'll throw a to do in here for a second because we're still working with this and I kind of don't want it highlighted in red. With that, in this case, comes the need to annotate collect in some way. The issue here is actually not that we don't have an annotation at all, but that it can't figure out what we're going to keep. So really what we're going to end up here is a vec of options of usizes because these indices are coming in as usizes. So there are two places we can look to see if we have kind of an iterator that does this for us, because we can just sit here and we can slice into it and keep going. But it is possible that there is, you know, a generalized version of that, which I think is somewhat unlikely to be in the standard library, honestly, but I will look anyway, just to show like what I do if I'm looking for something that I think could exist. Kind of not seeing anything in the standard library, which is what I expected. One thing we could do is dropping here. So we're going to loop anyway. And we could, as we increase this index, do a dot dropping and return that iterator, because that'll consume the first n elements, but it also doesn't give them to us either. So we need to find another way to do that. Looks like dot get could do what we wanted to. We would need to turn it into an iterator. And then again, we would also need to handle keeping around that other piece of state as well. So it looks useful in terms of like utility of it. So get, you know, some range out of the iterator. I don't think that it's actually what we need. Multi-peek is interesting. An iterator or adapter that allows the user to peek at multiple next values without advancing the base iterator. So we could do like dot next to get the next one, and then dot multi-peek on the rest of the iterator to peek on everything up until we get none back. I think in general, the slices are probably going to work out well for us because we can do dot contains on them. Not that we can't do that on the iterators, but we'll get to use a loop here. And unfortunately, this is going to run forever. So I'll get a break in here as soon as possible to get that to stop running. I'm probably going to have to kill my terminal over here on the left. The perils of infinite loops. And because I'm using NewShell, I can do a PS pipe where name is like cargo watch. And I'll just kill that process, hopefully. All right, and then we can get back into our test running here. And basically we're going to need to do this again somewhere in here. So instead of loop, we could also use while update.length, or not length. I always forget to do this. We can do while update is empty, not, then keep doing this. And then we don't actually need this break because it will stop. Of course, for it to stop, I can't redefine them again here. I have to set them. That was unfortunate. The perils of infinite loops. Okay, so then we get here, we have update with 4, update with 3, update with 2, update with 1, and then we stop. So I think if we get through this whole thing without needing to return, then we can use some index. I guess now that I think about it, we actually don't need this to be some index in the type as well. We only need it to be there because this will filter out with the filter map. When I wrote that originally, I was thinking of just using filter. And we can just debug results to see what comes out at the end, which in this case is everything. So we're not filtering anything out yet. So while the update is not empty, we need to take the current item, look up any rules for it. I guess we can use let else here. So let some pages equals rules.get else continue. Because theoretically, we could have a page that doesn't have any rules for it. And I'm going to stop using this little helper that I have. Recipe was terminated by signal 9. Yes, I terminated that. Okay, so we are not going to be using that helper for the moment because we need this to run once and I need to be able to cancel the process if it's taking too long. And with it behind abstractions like just and other things, that's not working. So no matter what happens here, we need to do this logic anyway. So we can do some logic if we have some, and continue to update our slices regardless. I feel the need to check the rule set again. So the rules specify what numbers must come after, but they also kind of implicitly specify what comes before. And my guess is we don't have a test for that. So I guess I'll just keep that in mind as we go through this. So instead of next pages, I'm going to call this pages. I'm going to call this something really ridiculous like pages that must come after, because all we have here is sets of pages. And there's kind of too many rules here for me to keep in my head. So like if we have 75 every other page, so everything in this slice, or this slice needs to contain all of these pages from all the rules. But that's not necessarily true. So I think we have to keep the befores as well, not just the afters. So I think I'll call this original update. This will be original update 0, original update. This let before pages be original update, everything up until the current index, which in this case is 0, which is awkward. So I think we just specify this as an empty array to start with. And then down here for this, we get away with not having indices here for moving forward. And I think we can still do that. So we're not original update. Before pages equals original update up until before pages dot length plus 1. And what is our issue here? I'm constructing an array. Is that expected array found reference? Because I'm trying to take a slice here. Oh, because this is not a usize. Wait, it's dot length though. Oh, because this is an actual array and not a slice. Right, so if we do something really silly like this, then we can have kind of an empty slice here, and then this will work. So it's just a type issue, really. So if we debug in here before pages, I guess I should name that after pages then. And we go up here, before pages starts at nothing, and then is 75, and then is 7547, and then 7547, 61. I think this is all right. This is always the before pages as we enter. So it'll be 75, 47, 61, the current item, and then the page after. But the page after gets pulled off, and then there's nothing after it. But we still need to check everything before this 29, I think. So the 29 actually needs to be, this condition right here is wrong. We need this to be while before pages is dot length. While before pages dot length is not equal original update dot length minus 1, I think is the correct while condition here. So we end up with before pages being nothing, then 75, then 47, 61, and then it looks like we still start the new one. Maybe I panic here for a second, just so that we can get a better, clearer view. All right, the very last before pages we have is a length of 4. So maybe I was wrong to do the minus 1, because the before pages should get everything, I think. Index out of bounds, length is 0, but index is 0. Right, index is 0 here. So actually, before pages logic will come first, then update, I think, can always get updated, and then we should see the same error. We could set this to be an option and know that we've unset it at the end. I think we can do if let some page equals update dot get 0, then current item becomes page, which is probably going to need to be dereferenced. So we're getting in with update being nothing. I think we put both of these in here then, because in that sense, if we can get anything from that index, then we should be updating the current page and the update, and otherwise we don't care. Okay, and then at the end, we have the before pages with everything in them. So that is perfect for us. And if we get here, we can return the index, which in this case is still going to be all of them. So now we need to do our checks, which is going to be update.contains, I think, pages that must come after that all. And then we end up with a page here, right? And that page must be contained in update. Actually, it doesn't need to be contained in update. It only can't be contained before, right? And then if we're good here, none of the rules that should come after come before, then we continue. And if not, then we filter it out. And our results say 0, 1, 2. Is that the correct set here? The first update, second and third, 0, 1, 2 are good. The other 3 are not. That is correct. And then we need to know the middle number of each. I'm going to assume that there is a middle number for each. We're going to take those indices. We need to look for updates index dot length over 2 plus 1. And then this is updates index dot length, or updates index middle. sum. Then we add them up, right? And then we have an issue here, which is that these need to be dereferenced. And we haven't typed our sum container here. I think that's the wrong type. What do we use? U32s? Look for the error message. A value of type usize cannot be made by summing U32s. That's great. We have U32s. We can use U32s. Looks like we have the wrong number. Are we supposed to be adding these? 61, 53, 29. So let me just debug the mids. 53, 29, 13. That's not right. So I'm up one because in the... Why did I feel like I needed to add one there? I thought we were going to get, I guess, integer division on an odd number. So just force this to error out. So we get 221. Yeah, I guess because we're using the length and it's already 0 indexed, then that number is the number we need. That makes sense. That's where our like theoretical +1 is coming from. So this runs. Hopefully this works, because I don't know about you, but I had a hell of a time keeping the rule set in my head. That's a gold star for us. Part 2. Yeah, I had a hell of a time like keeping the rule set for what we actually needed to test here in my head. And I guess we never needed to keep the later pages, right? We only work on the before pages. So actually this updating here is irrelevant completely. I'm going to keep it in for a moment while we look at part 2, just in case it's necessary. So the elves got to work printing the correctly ordered updates. You have a little time to fix the rest of them. For each of the incorrectly ordered updates, use the page ordering rules to put the page numbers in the right order. For the above example, here are the 3 incorrectly ordered updates and their correct orderings. I think we can just implement. The only question I have is what happens if there's a number that doesn't have a rule. After taking only the incorrect ordered updates and ordering them correctly, the middles change. Okay. So I guess 97 and 75. I guess this really only works out well if everything is correct. Is there only one incorrect number in all of the updates? I feel like there would be a lot of edge cases for this if it wasn't tightly constrained. So maybe we get to identify just the one that is wrong. I feel like it's telling us to only move one number. My concern with that is that I really just want to implement the full sort because we have all the rules. But if we're not supposed to touch things, then I hope we only have 1 to move. They don't show any examples with 2 to move, but I feel like this could easily get out of hand very quickly. So we need the updates that are not in the correct order, and then we need to modify them to be in the correct order, and then we need to add up the numbers for those. And the answer for that is going to be 123. So the only thing we're really doing is checking the pages before. I wonder if that's enough to correctly identify what we need to do. Of course, the issue here is now when we get to the success, we don't want that one. And if this fails, then we want the index and actually also the page. Can any of these have multiple numbers that are the same? Doesn't look like it. I'm just kind of scanning to see if there can be multiples of the same number, and stuff like that. Although this feels like one of those problems that is built to be very specific, which is kind of made obvious by the fact that they're all odd numbers. Like they all have a middle number, for example. So like there are constraints around the generation of the numbers. We just aren't told what they are. So we kind of have to guess and assume at what they are. So if we're going through and the only thing that is really an issue is if there are numbers before the number that we're looking at that need to come after, and we only probably need to find the first one that happens for, then this is not going to be a for. This is going to be, or sorry, this is not going to be an if. This is going to be a for loop. I guess we could do a find here, actually, right? So if we have pages that should come after, we can iterate over those pages. We can find the page that exists in before pages, if it exists, and let's test in part 2 and see what we get. It looks like 75, 13, and 13. This is looking for that page, though. We don't need this page. We need the current item, I think. 97, 29, and 75. Does that sound right? No. 29 and 75. 29 is correct, but 75 is not. So I think actually we can leave this back at the all, and this will be current item. This is the same logic we had before then. This is still giving us the wrong answer. So let's do all the pages, I guess. The current item. So for 97, it says 75 can't come before 97. Okay, so we do need to do a full sort. Okay. We do need to do the full sort. This is 97, 75, 47. I guess actually maybe not. Maybe 97 is the wrong one. So that moves. It doesn't change the middle. 29 moves. And then what's the wrong one here? All of them? 97, 75, 13. Yeah, I think that requires multiple moves. So our last one is 75. And 75, 47, 13 must come after. I think we actually do need to sort this. So we get all the indices, right? We have all the indices for all the issues. This is getting the middle point. So let's do results.iter. I guess we map the index into the actual thing that we need to work with first. Cloning this is fine. We're just going to shadow this as results again. Well, just name it R for now. So now we need to implement the comparison. I feel like my question is, even if we do sort by, are all of the numbers covered by all of the rules? And we don't know the answer to that. So if we clone this and we use sort by, then A and B are our comparisons. I feel like we have to key off A, but we could possibly also need to key off B. So like, I guess on some level, it's if we have rules, or if we have pages for A and B is contained in those, then it's less. So for that, we can use is sum and. Let's do that. Let's just do a random ordering here for a second. Right, it's entirely possible this kind of thing works. And let's just see if that sorts for us. I didn't return any of this, so I do need to do that. So updates, index, clone, sort by this, if rules this, then that. This is unfortunately mutative, so we'll go with update, and we need to return update here, which should theoretically give us some numbers. So let me copy this over. I'm kind of starting to get a little nervous about this. So 97 to 53, that looks correct. 61, 29, 13, that is correct. 97, 75, 47, 29, 13. So that's all correct. And don't worry if you don't understand this, I will explain it if it works. If it doesn't work, then it doesn't really matter. It looks like we need to do sorted results here. Sorted results is just going to be the results. So we don't need to do this like updates thing here, right? And then this should be a passing test. Perfect. We'll run that on part 2 and take a look if I can even hit the copy and paste button correctly. That is the right answer, which is wonderful. I love that we happened to get it. It may have seemed a little bit slow today, but I have seen problems like this, and moving too fast has gotten me into problems with Advent of Code, problems like this in the past, where there is, you know, a set of rules, they have to happen in a certain order. You miss something in like this paragraph in those words, and then it's like not what you thought it was, and then you spend an hour debugging it. So that was my true concern today, making sure that we followed all the rules correctly. I like sometimes it does things like not tell you whether just one thing needs to move here. Because like originally I assumed that we needed to sort this whole thing, but then I wasn't sure because it didn't say sort the whole thing explicitly anywhere. And that's the kind of thing Advent of Code has done in the past, where it doesn't specify something like that, and you find out that you were only supposed to move like one of the numbers. So let's cover this again. For part 1, we have a set of rules and a set of updates. These rules specify pages that need to come after the page on the left-hand side. So 13 needs to come after 29 here. These updates are not necessarily correct. The first 3 happen to be correct. So for example, all the numbers for 75 are either after or not in here. Same thing for 61 and 53 and so on. So the way we tried to do this is we kept track of a number as we went along and ended up checking to make sure that, say for 75, it had a vec of the numbers here that need to come after it, and just making sure that none of them were before it. So for 61, there's numbers that need to come after it, and we, for our validity check, made sure that neither of those numbers were 75 or 47, basically. I feel like I was almost afraid to look at our benchmarks today, but our benchmarks are fine. Our yesterday was slower for us, so that's 200 microseconds and 360 for part 2. So for us, the parser was the easiest part of today. I think generally speaking, you probably could have done this with dot split and dot lines. You would have had to split on double new line to get this gap, and then you would have had this, and then you would have had to dot lines this, and then dot split again. Same thing down here. So for our parser, we decided to break it up today into a number of sub parsers, which is one of the benefits of using Nom. So we have a parse function that takes our stringing slice as an input, and then we have our rules parser and our updates parser. For our rules parser, we decided to terminate it in a line ending. I also could have just like put this in between these two. I just decided to do it like this instead. And then we return the results of those two parsers, which happen to be a hash map and a vec of vex. So our updates parser, much simpler than the other parser probably. We have a separated list looking for line endings, and then a separated list looking for commas. So that's all of this down here. So then we get a vec of each of these vecs. Pretty straightforward for this one. For rules, we decided to go with fold many 1. That's because I wanted to build it up into a hash map again. One of the things that people do for speed in Advent of Code is not use hash maps, but use sparse vecs instead. But I'm not trying to squeeze every bit of performance out of this. Maybe you are. Maybe that information helps you. So we get fold many, which is just a fold. We have our parser here that will iterate repeatedly. We have the default data structure here that will accumulate into. This is going to be a function, so in this case, it's the default hash map. And then we have a closure, which gives us the accumulator. That is our hash map. The keys are the page IDs or the page numbers, and the values are the pages that should come after them. So we get a page and after, and then we get to use the entry API. The entry API is a really nice feature of hash maps in Rust. We can do .entry on the page ID to see if there's an entry there. If there is an entry, then we can push the current page that should come after into that vec. And if there isn't an entry, we get to set whatever that value should be, which will just be a vec with the after page in it. So that gives us 2 parsers that we can combine. That's parser combinators. And then for our processing, we take those rules and those updates. We iterate over all of the updates. So that's each of the lists of numbers that need to be in a specific order. There's some extra logic here that we don't actually need. Specifically, one of the things that I was doing is I originally felt like we were going to do the test on all of the pages that came after. So I was slicing and moving forward. This is just taking off, the front option of the slice every time we move forward. We do keep the current item around, which is really important because then we know what page we're supposed to be looking at the rules for, or what pages should come after. And then we use a while loop, which is fun. We take the length of the before pages because we are filling the before pages in as we move through and making sure that it doesn't match the original update length. So making sure that we haven't pushed all of the pages for the update into this before pages, because if we have, then we're done with this loop and we automatically bounce out and move on. I happen to be looking at part 2, so I'll switch over to part 1 quickly. It's the same logic though. We kept the same logic. So inside of this while loop, we can reach into that hash map with the current page ID, get the list of pages that should come after, iterate over those pages and make sure that all of them are not included in the list of pages that come before. If any of them are, then we return none. Otherwise, we continue with our loop, updating this before pages slice and also the current item in this like after pages slice, which we don't actually use the after pages slice. Actually, that's generally incorrect. The only thing we use the after pages slice is to get the current or the next item, which we actually don't even really need it for. Then if everything goes well, we pop out of that loop and we return the index of the update that we need to get the middle point of. And we can map over that, do a little bit of math, get the middle point of that update, and then sum them all together. Now in part 2, there really isn't that much of a change. We need to flip to looking for all of the ones that are breaking or the ones that are incorrect instead of the ones that are correct. So all of this logic stays the same, and we swapped to return the index of the ones that are incorrect and skip the ones that are correct. That's the only change in all of this code up here. That gives us our results index, in which case we get to map over each of those update rows and literally just sort it. Like sorting is built in as a function in the Rust standard library. So what we get to do is take advantage of ordering and the sort by function. Now, normally you would do like a .cmp or a .compare, but ordering is literally just regular enum. It's got less, equal, and greater. Normally to compare two things, you use .cmp, and that gives you the enum back. So that gives you, hey, this one is less, or they're equal, or one is greater than the other. Now, these comparison functions are usually provided by a trait called ord. This is the trait that lets you implement compare or CMP and lets you return in ordering. This is also where things like max and min can come from. So if you derive ord for your type, your number, whatever, which it is for a bunch of these, then you can compare them. So in this case, all we're doing is we're saying we're going to sort by and passing in this closure. And the responsibility of this closure is to return that ordering and determine whether it's less than or greater than. In this case, the way things work out, if there's a rule for the item on the left-hand side here, and the pages that should come after contains the number that we're comparing against, then the number that we currently have is less than the page that we're looking for. Otherwise, it's greater than. And that's just kind of an assumption here. This part right here could have very easily been an issue for us. We could have had to handle, equal to, greater than, whatever. But in this case, it was not. There also could have been an issue where like we needed to look up B's pages and then do the same check here the other way, but we didn't need to. So we took our vec, we sorted it using our closure, which just looked up the rules and sorted, and then we returned that. And then we have the same logic down here to get the midpoint and add them together. So that's it for today. Kind of very rule driven, I guess. Something that I don't know about you all, but I felt like I had to pay very close attention and spend a lot of time making sure that I was implementing the rules correctly. And I almost didn't even do that. I almost checked for the ones that came after instead of checking the after ones to see if they were in the before array or the before slice. So I think this could have gone a little bit smoother. We didn't really need to do any debugging because we spent the time making sure that we were implementing correctly, which is great. When we were done writing it, it actually did run and did give us the correct answer, which is always great. And now we have 2 more stars. So when we benchmarked, we got 200 microseconds and 360 microseconds. Not our fastest solution so far, but also not our slowest. And I'm very happy with the way that we were able to actually just flip the condition here. I think it would be pretty reasonable to pull this filter map function out into a separate function, and that would probably make this a little bit easier to read. I could clean up some of this additional logic, like this update isn't necessarily used for much. We could get this in a different way. So things we could do, things we could clean up, but overall happy. And I'll see you in the next one. Have a great rest of your day.